from NIT Goa. Before hand over in the session to Damodar sir, let me introduce about him. Presently, he is working in the Department of CSE, NIT Goa. His main area of research is in artificial intelligence, brain-computer interface, medical imaging, wireless sensor network, cloud computing, deep learning, information security, and many more. He has done
Hello, sir. Can you hear me?
Yes, sir, we can hear you.
Can I start the session now? Hello. Yes. So good morning, friends. This session we are going to discuss about the various applications of machine learning and some research challenges, how we can use the concepts of machine learning for solving some various real-time applications, and then how a problem statement can be solved with deep learning architectures, and how other machine learning models to be opted in the case of some requirement. So before solving, how do you define a deep learning architecture? Like, first of all, like, when I say that some computing problem can be solved using deep learning or conventional some perceptron models or other bio-inspired optimization algorithms and everything. Can somebody just comment on this? How do you say that, okay, my research problem is in need of some deep learning based solutions? Because when we look into the research problems where machine learning is being used, most of the problems people are trying to use with deep learning architectures, and some of them are of course using some other optimization modeling, etc. But how do you identify that deep learning based solution is one such a choice? Because nowadays selecting the suitable machine learning architecture is very important. How do you identify that, like, certain machine learning problem is really, I mean, a certain machine learning based solution is needed for this? Any computing problem I can use machine learning, or I have to use any other machine learning based architecture? What is your idea about that? Somebody share your views. Let the session be interactive. Please feel free to share. What I'm asking is, if there is a problem, some research problem where you want to use some deep learning based solution or some genetic algorithm, or some fuzzy logic based solution, how do you know that which is more suitable here? Somebody please unmute and answer. Just like any computing problem I can solve using deep learning, what is the first criteria to have deep learning in my model? Any answers in the chat box? No. Okay, can I say, like, if there is no training, there is no neural network or deep learning, obviously, right? If there is no training data, there is no neural network, there is no deep learning. Now, when to use deep learning architectures? Now, when we are solving a computing problem where some training is given, like some supervised nature, some supervised data is given to you, based on understanding that, we are going to analyze certain, untrained patterns. Like that's known as like how a super learning problem can be used to solve certain real-time problems. Now, when it comes to supervised, some training data is there. I'm going to use some conventional neural networks, some perceptron models and all. If the training data is there, I can say like conveniently I can use this neural network. And if the training data is there and I have some large amount of data, testing data, large amount of data. Normally, see if you can understand the basic functioning of neural networks, when such a training data is there, when we look into the patterns, when we get some similarities between them, and when we make this weight optimization, that aggregation and activation of values, feature values, you're going to get some conclusion, like which class it belongs to. Whenever the training is very, not sufficient, it is difficult to take the testing. So when sufficient training, some handful amount of supervised features or patterns given to you, now my job is to test in the next level, to make the analysis about the untrained patterns. Now, when it comes to the differentiation of using deep learning or non-deep learning based neural networks, we have to understand that in deep learning based architectures, normally we have some large amount of data, which it is difficult to encompass in, one hidden layer and try to extract entire information one layer. Normally, if you can observe, there is an input layer, there is a output layer, there is a hidden layer. Now, what are the neurons in the input layer called for? Tell me. What are the neurons in the input layer? Do we call them? They are features, right? They are features. So when we take up these features in the input layer neuron, we are going to extract certain information from them, certain knowledge from them. When we make the computing or the layered architecture happens in the next hidden layer, then we get some kind of values which says that what, okay, which class the label belongs to, or which class the pattern belongs to, and what is the most probable group for that. But when it comes to deep learning based architecture, since the data is very high, the data is very low. Normally, we take deep learning for some large data sets. When you take for simple data sets, it may not be very effective because you can solve the same with some conventional feed forward neural networks. So when it comes to complex deep learning architectures, normally the type of data we are taking is like very high in size. When you take very large size data sets, what happens? We are going to take some input layer features, and the features are, when you take up these features, the next level you are going to extract better and better features. But in the deep learning architecture, what happens? Since there are more than one hidden layers, when you are making that layer by layer architecture at computation, you're going to extract better and better information. Or you can see the knowledge discover, how data to information to knowledge. When you take up a conventional perceptron models, conventional neural networks, it will be difficult to get maximum knowledge discovery within one hidden layer. Hidden layer means for what? Learning, knowledge discovery, right? What happens during the hidden layers, or just one hidden layer in the conventional neural network? To take some input layer feature, based on that, some knowledge discovery happens where some class will be fallen into. In deep learning architecture, when it comes to, the knowledge that you gain in one hidden layer is not sufficient. You have to extract even further, better features. Layer by layer, what happens? You are extracting better features. The moment features goes maximum extraction of the analysis about the data, you end up with what is a probable class for the given data or given pattern, right? Therefore, when there is large amount of data, training data, large amount of data, some handful amount of training data, good amount of training data, then such a complex deep learning based architecture we used to select, right? So in one word, you can say like when there is sufficient training data, I go for neural networks. When there is sufficient data and training data and some large amount of testing data, I normally prefer to have this deep learning based architecture. If there is no data set, no deep learning, I can call it as like. Unless sufficient data is there, there is no point in going with deep learning based architectures. Okay. So before going further, confirm whether I am audible.
Yes, sir.
Yes, thank you. So now we are going to see plenty of applications in deep learning. Before that, anyhow, since we started discussing how to adopt some computing problem with deep learning architecture, when deep learning is not there, how come other machine learning models are useful? Just let us spend some 5 minutes time on that, so that we have a good motivation, like how a machine learning model can be chosen when we are into some requirement of a, I mean, solving a computing problem. Now, if neural networks won't be a choice, then I have to go with other models. Now, when neural network won't be a choice for us, tell me, somebody. Tell me, when neural network won't be a choice for us?
When we don't have training data.
Yes, when we have no supervised nature of the problem statement, because we are not got any specific idea about the nature of the problem statement. Therefore, it is difficult for us to solve it. You are right. Then my job is to explore other opportunities, other suitable machine learning model. Are you following me? It's very, very important to know, because some training data is very nominal, very minimal, not sufficient. Like if take a diabetic patient data, I'm training on some 100 or 1,000 patients. Like if his age is something, if he has, I mean, height is something, weight is something, he has smoking habit, drinking habit, etc., etc. Finally, his class 1 or class 2, whether diabetic or non-diabetic. So like that, second row talk about another patient, third row third patient, or some 100 or 1,000 patients data is there. I'm trained. If his habits are so on, so if his age is something, weight is something, height is something, he is diabetic or non-diabetic. I'm trained on that. Then I can easily say what is my possible class for an unknown tuple, like unknown record. Like when we say some person his age is something so and so, whether he is diabetic or not, I don't know. The predictions I can make using what the suitable machine learning architectures. I mean, suitable this computation I can have. But the question is, if the training data is very nominal, like only some 2-3 patients I'm trained on, can we say no? It's very difficult, because we should cover vertically, this vertically and horizontally. Only then we will be able, like more subjects and more features. Therefore, when training is not there, then I say neural network may not be so effective. Yes, right. Then what is the alternative solution? Now you have to understand first, what was the primary job of neurons? Neurons, somebody tell me what is the main job of neurons?
Transmit information.
They transmit the information, they communicate each other at light speed 250 miles per hour, neuron to neuron communication, and with those synapse junctions and all. But problem is, they're actually the main responsibility is not for transmitting data. They do this for learning. The main job of neurons is learning. Do you all agree with me? Neural networks, learning happens. How learning happens? By training. By training. So when the training is missing, then I cannot use neural network effectively. Therefore, I have to drop them and I have to go for other alternative solution, because though there is no training. There is no training, learning is minimal or zero. Then when learning is zero and there is no training, because now what is the consequence, you tell me? The consequence is searching is high. Please try to understand. When there is no training, learning is minimal, thereby searching is high. So enormous searching is required when there is no neural network based solutions are available. Why? Because there is no training was given. On the other, you want to say, if there is no supervised and support, so if there is no supervised data, you have to have a lot of searching, because obviously your supervised data means what is it? It's a hint given to you, right? It's a hint. It's a training. When there is no training, eventually you have to take more time. Are you following me? So it's very, very important to understand how this will happen. Now, if if for example training is not there, I want to go for other alternative suitable machine learning model. What are those? Normally, like I mentioned, when there is no training, lot of searching is involved. Then I would prefer to have some evolutionary computation model. Evolutionary computation model. this nature-inspired computation, bio-inspired optimization algorithm, genetic algorithm, swarm intelligence, this particle sum optimization, and all the others. Why? Because they are randomized algorithms. How do they work? We'll say if time permits. They are randomized algorithms. So in this randomized algorithm, it will be very difficult. There are some challenges in the randomized algorithm, but when it comes to the randomized algorithm, normally they are very, useful when such a training was not given. Therefore, it is very difficult to understand. It's very difficult to understand about the nature of the data and the type of similarities exist. Therefore, these randomized algorithms are very effective. Genetic algorithms, swarm intelligence, particle sum optimization, bio-inspired optimization algorithm. There are many. PSO, anticolony optimization, honeyfly, honeybee, firefly, grey wolf, artificial immune college system, and then grey wolf, spider monkeys, shuffle complex evolution, frog leafing, and spotted hyena, and octopus, dolphin swarm optimization, and plenty of the optimization, bat, binary bat, so many exist. So those we are going to see in the next level, because we need some optimization, because there is no training, because there was no learning, right? That's how we go with second category, because obviously, but there is some randomized nature, and these algorithms approaches talk about how to cleverly optimize using certain intelligent behavior. We talk about genetic algorithm using certain reproductive operations, crossover, mutation, selection, etc. Yes. Any doubts? Think somebody wants to say something. Any doubts? Mute yourself if you have no doubts. Next, third category, when we say now deep learning ruled out because there is no training. Evolutionary computation model, they are okay, but they are computationally expensive, but still they are good. A third type of model, when we talk about, normally they are different nature. Linguistic type information, fuzzy linguistic type information. If you want to process linguistic analytical processing, I want to measure somebody's mental state analysis. Like, I cannot say he's some 90% good, 10% bad, right? This type of linguistic analysis, when we try to perform, like whether a loan can be given to a customer or not, based on so and so features, what we take from. So this type of linguistic analytical processing problems, we normally go for fuzzy logic, type 1, type 2. Are you following me? So the third category is fuzzy. There are, different angle when we talk about. So normally, like that, many machine learning problems can be modeled subject to the type of data. That's why data analytics is very important when you go for dealing with identifying the suitable machine learning model, which are, because nowadays getting a data or getting a problem itself very difficult or very important. If I get my problem statement and half job is done, the remaining time I can, easily solve my problem. Getting a problem is a problem now. So once if I come to know that what is my problem statement, and if it is very easy for me to solve using the suitable machine learning model like this. Are you following me? It's very important to know how these people are, how the researchers are selecting certain suitable machine learning architectures and all. Now let us go in the first category, like neural networks, deep learning, and their challenges, various applications, and everything. Am I audible? Listen carefully. Yeah? Now, when we talk about the deep learning architectures, certain challenges. First, what are the challenges in the conventional neural networks, and then what was the job of the researchers when we started developing or understanding the biological neuron model. Now, with the moment it started evolving the conventional neuron models, it was evolved a lot in the last couple of decades of time. So when they started, particularly in the last 1 decade, huge or unimaginable growth has been seen in the neural networks world. So when people started understanding the biological neuron model, and they become apparently possible to develop a lot of models with the help of artificial neuron models developed from the biological neuron model, they will remain unsatisfied. Like, still we can do a lot, because just when we understood the simple neuron to neuron communication and then computing strategy, where the nucleus and the cell body of the neuron works, and how do they communicate, and how do they interface with the central nervous system via spinal cord, they started, I mean, thinking beyond, like we cannot remain satisfied with this small computing model which we have developed. Of course, neural networks, they are ruling the computing world nowadays. Then they started looking into even further. Can we do, I mean, beyond, I mean, that is out of the box. We can control the world with our thoughts, because when we can develop a lot of computing model with our thoughts or the real time, see, I mean, what you call that, models developed based on biological neural model, their dream has become like even higher, boundless. They started, I mean, working on problems where they can control the entire world. Like if you talk about autonomous vehicular system, driver vehicle cars, I mean, driverless cars, and similarly, a lot of other, I mean, high-end applications, Android humanoid systems, robotic systems, and then a lot of other high-end applications. Then they started understanding like we can do a lot using the this brain structures, and then neural networks, and then other computing paradigms. Then they started developing a lot of front-end applications for this one, front-end devices, hardware and software devices. I mean, hardware devices and some software tools, customized tools. Then they started exploiting. So let us go in the direction, like particularly in the deep learning direction, how people started using for a lot of real-time applications where they can imagine. As I've already talked about the deep learning architectures. Now, why do we require deep learning? I think I already answered this question, just recalling in a new dimension. Now, I have certain problem, certain data, some supervised data. I'm going to solve with conventional neural models. Now, when we talk about using that artificial neural networks, our job is to learn at maximum level. Like when we talk about learning of deeper level, computation should happen deeper level. And you cannot remain satisfied with one layer and where all the computation can happen and you will be able to get some kind of extraction of knowledge. Not sad, because the data is huge, real time, and then very complex. It is actually, you can say general, I mean, high-end version of conventional neural models when we talk about. Then how this such a deep expertise is going to be, I mean, modeled, how the layered architecture is defined, how the weight optimization is performed, and how the activation functions are developed exclusively for deep learning architectures, and how the aggregation functions are being used. All those things to be taken care here. I've already mentioned, like there is no data set, there is no deep learning. Normally, deep learning requires a large amount of data. So obviously, it has to be like there should be some handful amount of training and large amount of data, which will help you to make proper analysis into that. But when there is no data set, what is alternative solutions? And when there is no proper training, what is the alternative solutions and all? So similarly, there are plenty of other models exist in the machine learning: transfer learning, data augmentation, unsupervised pre-trained models, semi-supervised, and one-shot, zero-shot learning problems. Plenty of other models exist. Depends on how we choose them according to the type of problem you're investigating and the type of data available. It's very, very important. Now, conventional, I mean, neural network and the electric brain structures and the signal communication. Can you see the slide for the electrical brain structure or the neuron? Confirm, please.
Yes, sir.
Yes. See, normally when we talk about the biological neuron model, how a conventional neuron model works, I mean, this biological neuron model works, and then see, we have to understand. And when we talk about next level deep learning architecture, we should understand how the importance of neurons and neuron to neuron communication, and what happens if we capture the signal, and how we can use for complex these problems using deep learning. So normally brain, which is composed of millions and billions of neurons, in this each neuron normally they used to get electrical inputs or signals from different other neurons. Let it be some thousand other neurons around. Assume that. Now, when they are communicating, when they are speaking, obviously, when speaking means something, some kind of activity happens, right? Some impulses are being generated and added together. That is to perform a certain task of activity, which will give you a desired, reference or action potential or impulse to the central nervous system. So when these impulses are added and generated, they are leading to an electric signal or discharge known as action potential, like I said just now, impulse or action potential. Now what happens? These action potential, when we talk about these electrical signal, normally they jump from one neuron to other neuron at very high speed, like 250 miles per hour. Now these neurons, when are this communication when we capture, we'll be able to make a lot of real-time applications. We understand like this exactly the deep learning architecture, the computation happen, how of course it is evolved from biological neuron model. But when we deeper learning, let's see, when the neuron communication happen, like one to other neuron, because you're getting electrical inputs from about 1,000 neurons. So when you take up a decision like I want to, stand up, I want to sit, I'm making thousands of communications from neuron to neuron. Then I'm trying to make the possible, execution of a particular activity in the human body. So this all kind of example. Deep learning hasn't come from somewhere. It's just an evolvement of artificial neural models. It's a biological neural model when it comes to the picture, obviously. So how the computation happens differently. For example, I want to go to office today. That's a normal procedure. Now, when it comes to taking a decision of going to office, like today it's heavy rain, I have certain neuron thoughts, and today it's IPL match is there. I have other neurological action potential generated, and I have some other work today, some family function. So considering all these, like deeper learning, when we talk about the neuron to neuron communication happen with different impulse value, when you're generating such a communication, finally your body is coming to take a decision, your mind is coming to, okay, I won't go to the office today. So there are all kind of deep learning computation happens in your human brain. Now, if you take simple like, okay, I'll go to office today, I have no other, simply go office and come back. It's a single level learning where we talk about. And when the deeper level learning happens, the information extraction can be even better and you can have a better conclusion. So it's very important how such a layer by layer architecture happens and how it learns. Normally, the communication between neurons is chemical, though the signal that is being generated is electrical. It's a wonderful activity because when neurons communicate via synapses, when we talk about an electric signal is being generated from a chemical reaction, and you can imagine the concept of this one. Now, we talk about a lot of neurons and all. Now, the brain structures and all, I think is not. Now coming to deep learning. Why deep learning people are very crazy about? Because the publication has high chances, of course, I agree. And some 10 years before when we published the first deep learning paper, we have seen like deep learning has high acceptance rate because rarely people are adapting their solution paradigms towards deep learning. But when it comes to today's date, now almost every paper people are using deep learning, some neural networks, etc. It has become a quite common thing. And people are not even aware of what type of innovations or contributions that one can add to the deep learning based solution. There are plenty of other problems you can use or solve while you are dealing with deep learning architectures. And first of all, what is the so beauty or this good thing about deep learning when you're talking about? See, when we look into all the other learning algorithms, learning models in the machine learning or other any solutions, any other learning algorithms, when the amount of data or when the data size is growing faster again and again, more and more, normally the algorithm will always increase for every other learning algorithms up to certain state, certain breakpoint. After that, either you can see there is some decrement in the performance or there maybe same, there is no much improvement in the performance. Are you following me? Whatever the size of the data you are taking, any other learning algorithm, it will always increase the performance up to some level. If you indefinitely keep on improving or increasing the size of the problem statement, that is the data, certainly there will be some breakpoint after which your models won't improve much, the accuracy, whatever it is, precision, sensitivity, specificity, whatever it is, the parameters you consider. The performance will be whether dropping down or maybe constant, asymptotic at some level. Since then, continuously, whatever it is increasing the size of data. In case of deep learning approach, once you have sufficient training, harmful amount of training data, then irrespective of the type of data, sorry, amount of data, size of data, the performance is always going to be increasing somewhat significantly compared to the all other learning algorithms in deep learning. Is how it happens. It's very, very important to know how the deep learning based solutions are going to maintain or retain such an amount of performance as compared to all other learning algorithms. What is so beauty in it? The reason is, when you talk about learning layer by layer, the layer by layer learning, I mean, these paradigms, you should understand we are extracting better and better features. Like when you go for increasing the hidden layers, etc., next level, and we are going to get better feature extraction. Like if you talk about like filtering the water, we filter with certain filters, again we filter, again we filter. If you go with like, we're going to get completely different water. The taste of water gets changed, right? Even if you go again, the water taste gets changed. It's exactly like that. The filtering and getting better information extraction. But of course, too much, I mean, processing also will make you the data, I mean, lost its properties. That is a different case of scenario. But if, at the same time, if you keep on filtering, keep on extracting the information, suddenly you will end up with what? A location where you may not extract much from the analysis. But of course, we are not going to use that. Our job is to go to such a level where the deep learning can give maximum amount of accuracy, where we can remain satisfied according to our ceilings. Like I have got at least 90% accuracy to get. That's fine. Then I can start. But your conventional neural network may not give. Then I can stop. Okay, I will start with my deep learning architecture, and once I get 90%, I will stop it, and I won't take any other hidden layers. Or I won't go for any other processing because I'm done, because I got more than 90% accuracy, which is my ceiling, right? So normal deep learning, when we talk about, like I mentioned, it should have some good amount of or some kind of training data which is sufficient to train the unreliable patterns. Then we go with this type of deep learning architectures like this, and that's why it's called as a universal approximator, which will be able to help. But in 1 second, just. Yes. So why do we call as a universal approximator? Is normally when we talk about the deep learning architecture, we try to consider certain features in the input layer architecture, and we try to extract those features and the knowledge in the next level layer to layer architectures, and the features are combined and aggregated to the next layer, like from one layer to the next layer, one layer to the next layer. So you're going better and better knowledge discovery with, right? That's why it's a very good approach for dealing with lot of I mean non-labeled patterns, large amount of data. The only criteria is like if you, because this type of models are computationally expensive. If I want to minimize this computational I mean complexity, or making the computational efficiency in this model, maybe you can start with when there is large amount of data, you need to take with all the patterns, that you can take some feature extraction, and then take the input layer features or the neurons from some kind of bind spread optimization algorithm, BAT, binary BAT, etc., where you can extract those features and use it for this analysis. And in fact, deep learning itself we can use using some stack of autoencoders and other complex I mean architectures, where you can extract these features or make the dimensionality reduction. Now, deep learning for classification when we talk about. Like I mentioned, there is more than one hidden layer is required because the learning that we are trying to ensure via the hidden layers of the deep learning or the neural network architecture is not sufficient because the data is very complex in nature, and at the same time the large value patterns exist. Most of the information we cannot extract in one level. Therefore, normally we try to use some multiple layers, and then each layer we try to make some weight optimization, feature extraction, and next level better features, and then go on next level, next level. Now, when we talk about using, because features design the notion of the classification, right? When we talk about such a features, it is very important. Like if we can manage to get with the better features, our deep learning will conclude at the earliest what is the best possible class for run output, right? So if you will be able to make some kind of feature extraction model and use those features in the input layer, then that could be one solution. You are making the feature extraction outside and using only those features in the input layer neuron of the deep learning architecture. That is one way. You are making it outside ready, and it is like your precast technology, like precast features. And when these precast features are not available, you can do, you can use deep learning with some stack of autoencoders. Deep learning with some stack of autoencoders. Like each hidden layer has one stack of autoencoders. Then what happens in these deep learning architectures? Hidden layer 1 has some autoencoder 1, hidden layer 2 has some autoencoder 2, and so on, so on. Using these stack of autoencoders, and we try to train them in a supervised way when we go with some layer by layer learning. And here what happens, each of the hidden layer here, what happens, since there is the autoencoder 1, here the number of features we are trying to reduce by passing through each autoencoder. So when we pass the features through each autoencoder, we are trying to extract better features, are known as your dimensionality reduction kind of. The output of the autoencoders, when it comes to, they are provided as an input to the system, or you can say the next level, maybe another layer autoencoder, whatever it is. So because when you are making this supervised learning layer by layer with stack of autoencoders, you are going to extract what minimum number of features which are very crucial. The question is, how do you automate, how do you make this learning happen? That is very, very important to understand. So using of this autoencoder based dimensionality reduction or feature extraction, feature selection, use in deep learning architecture. Nowadays, many of the researchers, what they're doing is like they take some existing deep learning architectures and they take some stack of autoencoders. Then, like they say, stack of autoencoders, or you can say deep learning is stack of autoencoders for some processing of so and so, like COVID-19 chest X-ray data, or some brain MRI data, etc. etc. Some, not exactly, just small data sets. They're trying to take, and they're trying to extract some accuracy, and they publish a paper. They're good framework papers, but you're not making any technical contribution here. And you never developed activation function or aggregation function, or you've never done weight optimization and etc. And so that's not a, I mean, great contribution from either of the side, but at the same time there could be a good option for this, how we can solve those technical problems using this. Many of the papers in deep learning, they are mostly, actually speaking, they are some framework oriented. Like there is some convolution neural networks, there is some fractal net, there is some AlexNet, DenseNet 121, 120, SqueezeNet, Pix-to-Pix network, generative adversarial networks, AlexNet. Plenty of models exist, which you normally see. And then we try to make some small variation in the model, or many of the time people are not making any changes. It is like a new framework. Somebody has developed an architecture like FractalNet, AlexNet, DenseNet, like that. Then use for some medicinal data, some kind of medical imaging data, etc. And they call it as like we are done. But that is just a framework. You are taking, it's nice package you are done. Like there is a model which was not uploaded on some MRI data. There is a model which is not uploaded on some kind of other data. They are taking it, and it's just a framework paper that normally it should be done by some UG level students. Even some of the projects of BTech level also, they're very good. So normally this type of framework paper should not be encouraged, but when it comes to the picture publishing a paper, that will do, of course, today date. Next level, when we talk about we want to make some contributions in this one and all, we can do. There is some theoretical contributions always possible in the layered architectures. You can propose different type of architectures by making them layered changes, computation connections, and then how to increase the learning rate. Many of them exist. It is very important to know how you are going to make some kind of contributions. You can develop new aggregation functions, novel activation functions, and you can propose new optimization algorithms which extract the better features, and those features you can use in the input layer neuron of the deep learning architecture. And plenty of them. For example, then there is one such activation aggregation function shown in the figure. A slide is a multiplicative aggregation functions which we are going to use, and then normally this multiplicative aggregation function we are trying to use based on some correlation between the features. When you talk about normally there are two types of weights when we talk about for input to hidden layer connection and similarly for each neuron to the hidden neuron, the input neuron to hidden neuron. So here what do you mean by taking or incorporating the correlation between the features? Is when you talk about different features exist in the those layered architecture, if you can nicely conveniently identify the correlated features, it is very useful for us to minimize the number of features or to optimize the features. To highly correlated features, I think you can take a conclusion onto this one and you can try to minimize the number of features accordingly, right? So it's very important. Like this is just an example of convention, kind of aggregation function where you are adding the flavor of some correlation between the features. By doing so, it is easy for you to deal with certain features and their aggregation, how they are happening. Like similar features, when you are aggregating them, you should have certain opinion for that. Other features, when you are dissimilar features, there is no much correlation between the features. So you are giving certain weightage in the aggregate while aggregating some features which are having those correlation. Highly correlated, not correlated, something like that. So here Vij represents the weight from ith neuron to the jth neuron. Obviously, they are not equal. The double J represents the weight from the jth hidden neuron to ith hidden neuron, R hidden neuron. And rho represents the correlation between the features Xj and Xj, rho Ij. So now, when you are making such a correlation, it will be very easy for you to talk about certain conclusions in this one. And when you are identifying the feature, some knowledge from the features, it is easy for you to make all this. So now we talked about the motivation to machine learning and then lot of other applications. How to choose a machine learning model and which instance we have to choose deep learning based architectures and other machine learning based models, soft computing model, other soft computing model, and then the importance of deep learning and the definition, and then we talk about the structures of deep learning, autoencoders, dimensionality reduction, and kind of technical contribution when we talk about deep learning. And many we have seen, now we are going to see a lot of applications. Before going there, like similar to the proposing a deep aggregation, we can propose new activation functions. Similarly, we can propose new activation, new aggregation, and we can use feature extraction. You can propose some improved autoencoders concept here in the deep learning architectures, and similarly, you can find a lot of variants of this existing deep learning architecture, like take convolution neural networks. There are plenty of models exist like variants, fractal net, AlexNet, DenseNet, like that. We can make some other variations and publish new architectures. So, so they're all about deep learning based solutions, convolution neural networks, recurrent neural networks, and plenty of them. Before we go there, just a small some number of applications which people may use, some basic applications, some advanced application we're going to talk about. Can you some can you have any doubts? Any doubts so far? Now we are going to see a lot of applications. If you have any doubt, let me know. No doubts? No doubts? Can you hear me?
Sir, you're audible.
Yes, no doubts, not even a single doubt, because now we are going to application side. Some 10 application at least I will show, so that at least you can just think of working on them.
Yes, sir. Okay.
Okay. So now when we talk about this deep learning based architectures for so and so real time applications, there are plenty of applications exist in deep learning. Mostly wherever such a complex data exists for you, where some minimum amount of training is given. Normally, there's it's a never-ending application we have using deep learning. Some of them, like mostly, we are going to see in image processing, some and some other applications we are going to see. Object detection and image segmentation, they are one of the well-known problems, some old problems, very conventional. Here, normally, we have an input image, and our job is classification. And our job is first to see what and all the objects exist in the image. A group of objects exist in the image, and we try to extract those objects and trying to separate them and call them as the segments. So normally in image processing, this image segmentation. So what I mean by image segmentation is nothing but a kind of unsupervised learning when we talk about with respect to this without object detection. Here what we do, we are trying to segment the images of different objects. Like what if there is a sheep, if there is a dog in the figure, if there is a person or some human being, we are going to segregate them, all these objects. Then once they're segregated, then we are going to extract them from the background and going to call them as different segment in the figure. Because that is very important. Image segmentation is one of the prerequisite for many of the image processing operations. Like I go to a shop and say that like at a Photoshop or somewhere, and I want to extract some background information, and so that I can make certain changes in the particular front end structure of an image. So in object detection, normally, like I mentioned, first we have to go for object detection if you want to make an image segmentation, because it's without identifying the objects, it's difficult to make the segmentation. Like you're coming close towards segmentation once you identify the object detection, because like if you identify the object of a dog, which means your job is to extract the exact contours or the edges of the region which is represented by this one, and you can simply extract this one. Then you can make a different colorization for this particular portion image which is identified here. Similarly, other objects which I can identify their presence or occurrence and then extracting from the background and colorizing them. So it's very important. Now, which is very difficult, object detection or segmentation? Tell me, object detection or segmentation? Which is very difficult? When we talk about detection, object detection, since sometimes many of the objects have similar properties, like if a dog and a sheep, if the height of the dog is a little bit, high, can you imagine like more or less the features of them are almost same. Some features are different, of course, but it is challenging to extract these particular objects, right? And similarly, when we talk about certain objects which are close by, it is difficult to extract them. The features are not so enough to be trained. And object to object, the behavior and the features or characteristics, they get changed in the image. Therefore, it is very difficult to make such an object detection. Once the object detection is done, it is easy for you to make the segmentation, because hardly now if you take about an object identified as the dog, hardly now you are challenging is only between the background image and the dog, the particular portion which you have identified. You can make some pixel intensity values and etc. Some kind of correlation, and you can extract it by not so concurrent, because you already trained enough. Your deep learning architecture was already trained on dealing with such a complex object detection on various different complex images. So it's not so difficult to deal with. Once you identify, once you identify the objects, then we can see like extract this particular object features from the background and then make a different colorization for that. But object detection is very difficult compared to segmentation, because segmentation is the next level of post object detection. Okay. So similarly, image colorization problem when we look into. Can you see the image colorization slide?
Yes, sir.
Yes, now there is an input image given to me. There are two different examples shown. One each row indicates one different example. So there is an input image and our model. That input image is just a black and white gray level image. And our model is going to produce a colorized image of the same. Right? Means what? Not just going to colorize the image. When the image was captured, what was the actual color of the deer that exists on the figure? It's not just some random ad hoc color I can give. No. What would have been the actual color of the object in the image when it was captured? That is a challenge here. So now by taking some possible predictions and some correlation with respect to feature and intensity values exist in the background color image, this gray level image. So you can make some prediction, and you can say conveniently like what, okay, this could be the possible color of this certain region of this one, because it's not like object detection or segmentation, but it is when you are going to colorize like a different part of the or different part or different region of the images are different. So it's a kind of internal segmentation you are making when you talk about like colorizing the horns of this deer. They are into like black. Now they may not be too red or pink or whatever it is. So now I'm going to first of all identify this particular as a different segment. So indirectly, certain kind of you have somewhat connected to say segmentation or object detection there at the end, but that is about a particular image which you are trying to colorize, the portion of the image. Now here what happens by making such a correlation assumptions with respect to intensity values, with respect to pixel values and other criteria, you are going to make some colorization. But you should make sure that what it is as good as the actual colorized, I mean actual image which was captured in color when the object was there. So first column indicates the given image, second column is the colorized image of the actual given image by your model. Third column is the actual image, actual color image which you have converted as a gray level and given to your model. That is the first column. So now when I say that my deep learning architecture is very accurate, you tell me when I do say that my model is very accurate.
When the colorized image and ground image.
Repeat.
When the colorized image and the ground, when the real image are same.
Yes, when the second and third columns are exactly same, I would say my model is perfectly colorizing an image which was, I mean, which is black and white, gray level image, and it is going to say that what I'm going to extract like, I mean, all possible features so that I can make the colorization in effective manner. Now, if you see the first row and second row, which example our model, like the model which is used for this colorization problem, working fine? You tell me. First row, second row. First example, second example. Which one it is showing effectively?
Second one.
If you see second one, second example, I think it appears that both are having the same, I mean, exact images, actual image and after colorization. When it comes to the first image, if you see there is some clear change in the background and the color of the deer that is there. So certainly it is very important to understand. Of course, I don't know how far you can see because the screen is shared. Now you may not be able to have a lot of font properties retained in your screen sharing. Therefore, it is very important to know. Then it's talk about changing such a characteristics would be very difficult. The image is challenging. Now, similarly, other example, photorealistic style transfer. Now there is an input image, original image, and I'm going to give one more image also to the model that is just a reference image. I'm not going to do anything with that image. I'm going to take some properties from that image, some reference. That reference I'm going to add in the first image. It's known as photorealistic style transfer. Are you following me? So in this photorealistic style transfer, the second image which I have taken, that some reference I'm going to take and adding in the first image. Now, if you see the first row, first example, what is the style we have transferred to the first image from the second image? You tell me.
The first was a
First row, first example. What is the reference or what is the style we have transferred, that realistic style transfer effect we have done into the first image? What is that style?
the petal, what is it? The petal design.
Can you repeat, sir?
The petals design.
No, you see, sir. First column is the input image, given image. That I am going to change. How I am going to change is depending on which style I am taking from a reference image. Second column I am going to take an image.
Oh,
That image just I am taking a style, some style that I am going to add in the first image. Now, which style I have added here in the first image? You tell me.
oh, then this is the color.
Yes, color is the style we transfer. That's why we call it as a realistic style transfer. It's realistic. It is existing in some image we have taken as a reference. Now that we are adding in the first one. It is very important to know realistic style transfer.
It's also the water transfer, sir.
No, that is not done. But now I'm going to ask the question now. Here, if the color of the flower in the first image is maybe yellow. Now second one is maybe maroon or red. Now the color I have transferred. Similarly, any style, like when we say some image is there, reference image, it's called as a reference image. From the reference image, I can transfer any style exists in that. Now here, what is the style I transferred? Color. Similarly, if I can transfer any other feature, I can transfer here, and any other style.
So that dew drops. That,
So here what happens, I can transfer like other feature, like the flower has certain water drops into it. Like what? So if I transfer that style, it's not just a color, not only color, I can also add some water drops. I don't know whether it is added or not, but if you want, you can make a like this is important. You should know what style we are transferring. First, we have to decide from the reference image how many styles we want to transfer. Is only one or multiple styles? Accordingly, we can decide. So the color we have added, maybe water drops also you can add in case you want. It's not true that every property you have to add, but at least one reference you have to take from the reference image. Now take the second example. Second example, there is an input image, original image, there is a reference image. Both are given to our model. The third image is the result, that is the changes we have done in the first image. Now tell me, what is the style we have transferred to the first image from the second image?
the lights, night lights.
See, if you can observe, these two are not the same images. First image is different, second image is different. Two different cities, assume that. First image is captured daytime, second image is captured nighttime. Now our job is taking a reference from the second image is what? If an image is captured in the night time, a city, it looks like this one. What happens if the first image, which was of a particular city location, if this is captured in the night time, how it looks like? You're not capturing the night time, you're converting, you're adding the style into this image. If it is captured in night time, it will be like this. That's called as a photorealistic style transfer. So you're reconstructing an image as if like how it looked like if it appears to be. Are you following me?
How is this done, sir?
Yes. Now the question is how it is done. Now when you are doing this one, first of all, see you now your question is like second example you take. Reference image. Some buildings in the night time, some texture, how the texture look like, how the pixel values they are going to be changed. If there is a building, like we can identify some structure in like object detection. What is the object here? A building, right? In the both the photos, what are the objects? Mostly the buildings, right? The heights and all that. Of course, they are different buildings. First, I will take one object, some object. Now I'll take object in the first image, which is captured day night, object in the second image. They'll compare. When you compare with the second, when you compare with the second one says their pixel values are different, their texture is different, their intensity values are different. Why? Because that image is captured in the night time. If you can observe, daytime the outside portion of the structure or object is having high pixel values, where in case of night time, are you following me? Nighttime, when you take up the inside of the building, when you talk about, they're having their pixel values are dominating. If you can observe, not exactly, just giving a kind of rough idea to you. If you take up two objects in this and compare, day night, if you can see, if you just take a window and see, day night you can see outside what is happening, night time outside you can see what is happening inside, if it is a transparent mirror. So they are going to be complete different properties if you can observe. Do you agree with me?
Okay.
So this type of that image analysis we have to make, and object to object, when we are comparing some features we are extracting. If this is an object in a particular image one, if this is an object in image two, referenced object, how the features are going to be differentiated here. Then we are going to make the transformation in the next level. So of course, behind we have some object detection, object analysis, and then some enhancement and some transformation function. They all exist. Front end you have what? The reference I am taking and I am comparing with the objects of the other image and how the values are going to be changed and how the transformation is defined. Then the values are going to be transformed of each of the pixel in the actual image. Then finally you are going to get the image of the the first picture, how it looks like if it is captured in the night time. So you are mapping the properties of the second image to the first image. So there will be a transformation, there will be a segmentation, there will be object detection and everything.
Properties in the sense you mean the features?
Yes.
Okay, so we are extracting features from the reference image.
Yes. Now obviously, now if you take this first image, see now this image is what both images have colors, first and second image, the flower, but the feature of the second is different because it has completely different color. So they're completely RGB and all your pixel values is completely different. But you should have idea when you take up second image, you have all the information about the second image, pixel, so on, so location, what exactly the pixel value, and you'll make some analysis, you'll make some features and everything. You're trying to transfer this one. See, effect is nothing but a feature, right? What do you mean by transferring a style or effect? It is like a feature you're transferring.
Okay, so we're transferring the features.
Yes, we are transferring the features. We identify this image, how it looks like, what are the features, if it is captured in the night time, how it looks like, how a structure is looking like, and what is the average, what is a pixel value in a given particular region of location. Then how we can convert to this one. Their values are different in the actual image, and how the features are going to be reflected here, how the transformation happens, and how the classification of these particular this one objects happens, image segmentation, everything is that's why it's not a simple application. Behind that, lot of image processing. I'm giving only front end to you just so that you can go back and work onto this one.
And will you talk about this, or how to extract features? Can you talk?
Now, for example, you just take for sample, just I'm giving. Now, when we take a particular object in the image one, like some geographical location, some small building. Now, if I take other object in the reference image. Now, when I take these, now what do you mean by feature in image? It may be some edges or contours or kind of pixel values exactly with how they are going to change their values according to the location to location. So I'm comparing these two. Whenever I'm comparing these two, I'm going to get if there is an object, if there is an edge, if there is a contour. You're seeing that all these level sets and wavelets and all. So if I take a contour, first I will make the contour detection. Once I identify the contour detection, within these particular two contours of different object, how the pixel values are going to be changed, what is the average pixel value, and then if there is in between, there is different, like if you can see the building, there is in between lot of other inconsistent pixel values exist because the building is shown like with the outside portion is shown with different values and inside portion is showing with different value. So how I'm going to compare these two pixel values? And then we are going to make the features like if there is an edge, what is the adjacent value, and then accordingly how we are going to compare these two. So first you identify two different objects in these two images and make a pixel to pixel comparison. And then if this is captured in the night time, how it is going to be appeared in the particular pixel value. So all this comparison you have to make. Then you have to define a transformation in the original function, which will talk about all these feature values. Here, but obviously it is definitely not going to be exactly like if the same image is captured in the night time, how it is definitely, but with human perception we will not be able to see by, because mostly when you're comparing with the reference image, you're going to match the pixel values or everything with the reference image, but mostly to the outside world it look like same. So the question is how you are transferring the feature value and how you are going to optimize them. That's all. Can I go next?
Yeah, yes, sir.
Now other applications like object removal. Now there is a original image. Just I'm training my model assume that there is an original image, there is an input image. In the input image, some particular object is erased. Assume that. Now my job is I'm going to reconstruct the image such that how the second image look like as if the object is missing there, as if like the object is not there actually. So it is like a image you are reconstructing by deleting certain portion of that. For example, in the previous that image segmentation example, the same image if the dog was not there, how the image appears to be. We are going to reconstruct them. Now tell me what is the main challenge here?
Fill the pixels behind the object.
Main challenge is when you are reconstructing. See, previous case is just there is existing object or region of an image which we are trying to add some reference, some features. That's all. You're not changing any structures or any reconstructing the image. You're not reconstructing. You are just making some properties changed in the image. The previous what you call that style transfer. Here, when it comes to here, there is a image with some missing object, and you have to reconstruct the image by deleting the object region completely, such that you have to the image should look like if the object is missing is not there, how the image look like. So mainly you have to reconstruct the background of the image portion which is missing the object region. So if you take that there is a flower vase on some particular table, small table, if the flower vase is missing, how you can reconstruct the image? So if it is not there, then you have to see behind the that certainly there is a region, or there is a image region, there is a particular object behind the flower vase, but that was hidden while capturing the image. So when you are removing this flower vase, how now your job is to go back and reconstruct the actual missing image because there was a flower vase in the actual image, that region was not captured. Now how to reconstruct that? Again, I'm going to take some features here, like there is an object region, which is missing, but at least you have the entire surrounding that when you identify the entire contours of the object missing region, that like it appears to be like a curve, just an edge like a flower vase. When you see the surrounding features of that one, if you can see there is a window behind that, the region which is covered by this flower bouquet or flower vase, there is a window there. It may be a window or a door. If you can see the reconstructed image, it is the window or a door, you tell me? It is constructed as a window or a door?
It's like a window.
No, in the third image, it is constructed like a door. If you can see, this is door. But since that particular region is covered with this particular missing object, it could have been a window also. We are not sure. But taking the features, like if you can see that when you identify the contour of this missing object, if you see that particular the adjacent regions or objects are what, like there is an object appear to be like a window because your train may be a door or a window, which means you are already trained. When you are training your model on some hundred or thousands of images with this object removal, which you are intentionally blurred an object and asked to reconstruct, you are trained that okay, if there is an object appear to be like this and adjacent to your edges or contours, if you can see it's like if you can see like see, if you know the length of that one, if you know other properties of that one, or if the window has certain grills or sorts of properties, features, when you train them, it appears to be okay. This may be a window, or this may there are no grills noted. Maybe a door is noted. Maybe some wood portion is noted. That is the reason. Maybe it is because of this. It could be a door-like structure that was plotted in the third figure, the final output figure generated from this one. And similarly, if you can observe, there is some stairs somewhere which is to be intercepted with respect to this one. Therefore, therefore, maybe you can continue the entire like the particular region which is continuous either sides. Similarly, there is some grills are there. You can reconstruct, but the design of the grills, how do you know? Already you have certain reference with the previous side. I mean, with the with adjacent to the contour of this particular missing object. So seeing the same design, you can reconstruct. It's all about features and training and learning. It's all about taking the, so this will change from image to image, of course, obviously. So this is known as object removal problem. Now on the other side, we have image completion problem. In the image completion problem, what we do? Image completion problem, we have an image with some missing object, or not a color object, missing region. So I'm going to reconstruct this one. How reconstruct? Certain, for example, if you take a fourth image, just some simple example I give. If I take a fourth image, the person has some right eye, left eye is missing, right? Can you see this?
Yes, sir.
Yes. Now, how can I construct his right eye? Because I have to complete the image. All the missing regions should be completed now, reconstructed. Tell me, how can I complete? Because now I say most of the persons, like, it is symmetric. The facial structure is mostly symmetric, not 100%, but mostly symmetric. How left eye look like? Mostly right eye also look like same. So maybe I want to convert his, reconstruct his right eye by taking the reference from the first eye. It is like internal photorealistic style transfer, if you can call it, kind of. You have seen the style transfer, right, in the previous slide. Similar way, the same eye I can construct on the other side because it is mostly symmetric. Not exactly, just in giving a rough idea how to do that. But what about other portion, like now other portions like his complete nose and mouth is completely missing. Then how to do that? Because now it has no reference. At least eye has a reference. Other eye. Nose is only one. Mouth is only one. But it is missing and there is no reference. How to do that? Can we call it as the problem of the previous object removal? Or something like that? Not exactly. Now there is some object here that is missing. Now I am going to reconstruct something like that. Not exactly. Now here this is a person. Now something is missing. I am going to reconstruct by taking his adjacent features what is available. If the person's cheek is like this, if the person has this much fair complexion, if the person has this much big, forehead, how he's possible. Like some training, obviously it may not be same as compared to the actual photo that is being captured when it was not completed. Are you following me? So image completion is now, it is very challenging problem. Image completion is very challenging as compared to other, because here it is very important. Now this is also kind of almost like image completion problem only. If I give this one input and I am going to make, now tell me here, can you map this image completion problem? Same image completion we talked about. Now in this example, can you talk about image completion problem? Same example. Are you following me? We have defined object removal. We have defined image completion. Now in this example, can you tell me what is image completion problem?
Fill the missing part.
What is a given image? What is a given image? First, second, or third?
Given image is the first image.
No, given image is the second image.
Okay.
For object removal or image completion, whatever it is. Now for object removal, what we have to, we are going to construct the third column, right?
Mhm.
Right? Second column is given, third column we are going to construct for object removal. Now for image completion, what is given and what we are going to get? Tell me. Image completion, second column is given, and what we are going to construct?
Oh, okay. In the first column.
First column. Same example. There is a, see, like there is a blurred image, something blurred portion, missing region. I am going to reconstruct. I am going to get a flower watch here. So that's why it's challenging compared to this one. Object removal, image completion is challenging because object is simply you're removing and reconstructing based on neighboring particles, neighboring pixel values and other features. Image completion, you have to reconstruct what is missing there. You're not missing something. You're coming back or getting back something that is missing. So that is very challenging as compared to the other models. I mean, other problems. Similarly, we have some deep fake network, some fake application identification, and etc. Some photo is there, but taking some inherent features, I'm going to understand which is actually fake and which is something like that. This requires a lot of features-based extraction to be identified, and accordingly, we are going to see what is the exact feature which is missing in the actual image, which is suspected to be a fake image. And the features plays very important role here, very important role, because some video processing manipulated file can be easily captured with this one. And another important image applications like multi-domain image to image translation application, where there is a input image is given, just one image is given, and there are hundreds of features exist with respect to this multi-domain image to image translation. Here, how a person look like if he has blonde hair, how he looks like if his gender is changed, male to female, etc. And how he looks like if he's aged some 10 years younger or 10 years older, and how the same object or person look like if he has pale skin, and same person how he looks like if he's angry, happy, fearful, etc. And similarly, if there is any same, and these are some of them are shown. Similarly, there are 100 features exist. Style you can call as a style transfer or whatever it is. This is not exactly like a style transfer. This is different. Like there is an input image, we are adding a lot of, is not just a one style, we are adding a lot of features and we are going to select. Accordingly, the input object is going to be completed. So this multi-domain image to image translation is very important. There is a lot of application we are going to have, where we are going to understand for this different images we are going to capture, and their features are going to be manipulated, or you can say updated, with the help of which we are going to capture all these modified images. Is very important. There are plenty of applications. They can be. Can you tell me somebody what are the applications of this one? Some of the applications. Any application? Am I audible?
Yes, sir.
Yes, just one application of this one. I give an input image. I want to see whether how the person look like after 20 years, or how the emotion can be identified, or how he looks like if he's changing his appearance from male to female, like that. For example, if you got a photo of a terrorist which was captured some 10 years before, we don't have his latest photo, then what happens, we can capture that photo. I mean, we can add this multi-domain image translation in this with a feature like age 20 years older, and if he's wearing with different type of appearances he has. So he's 20 years older now, where he's having different, so he's going in a different get-ups, how we can identify them, so that it may be used for some defense or some forensic applications, right?
Right, sir.
Yes, and similarly, plenty of other real-time applications and VFX movie, computer graphics movie, etc. We have seen the Titanic movie, right? In one shot, when Kate Winslet was shown very young age, then same shot is transformed to the age when she becomes 90 or 85 years and 90 years old. That is how. That is because this image-to-image translation, multi-domain translation, or photorealistic style transfer. This is actually generalized version of the photorealistic style transfer, to say frankly. Actually, why? Because, but here the number of styles are like more and more like available. We have to choose a style and we have to try. It's not just we are giving an image reference image and all. Just we are taking the feature. They are like we are giving a feature reference, and that we are going to be converted accordingly. So mostly it is used in some VFX and some this graphics movies like the Bahubali and all others, and then we use it for some real-time application, many other like. Similarly, if you have like an image captured in the day in the wind summer of a particular geographical location, And if this is the input sun image, how the AI generated rain image after 1 year, 2 years, 3 years. This is just to see the atmospheric changes and some weather monitoring, weather forecasting, and then pollution changes happening in this one. By next year, how this is going to be changed, this particular location, how much greenery is going to disappear. This is all about. Like, it's not just image processing. Some atmospheric conditions we have to consider, some pollution rate we have to consider, and then last 10 years, how much change it happens. Those images we require for training. All those things. Are you following me? So there are all kind of applications. This is like a prediction. Now, if you take this Antarctica and all these glaciers, that ice, how they are going to be melt with some, exponential growth. And if this is a glacier or an ice plate, how much it is going to melt after 1 year, and how it looks like, and how much impact. All those AI generated image we have. Similarly, unsupervised image, not only same category. If I give an input image of a cat, AI generated images of different categories but similar properties, not the same group. It's unsupervised translation we are going to have. Same image appearance for what you can say cougar, cheetah, leopard, lion, tiger, but they belong to the same type of class, right? So similarly, NLP also has a lot of applications here when we talk about, but that's fine because we have got the time now. So now I will leave the session for any question answers if you have any. Now we have talked about plenty of applications. Let me know if you have any doubts now. I think some of you are answering in the chat box. Yes, you're all right. Crime investigation application, healthcare industry, modeling. Yes, there are the applications what we talked about. Yes. Any doubts?
So,
Yes.
okay. Um, when there is limited training data, you said we use this evolutionary optimization of the results, right?
Can you repeat?
In when there is limited training data,
Hmm.
we use evolutionary optimization techniques, right? Like genetic algorithms.
Yes.
Where do we use them and which part of it?
I mean, where to use in the deep learning or where to use in general you're talking about?
Where to use in deep learning?
See, deep learning, for example, now normally we have mentioned deep learning has some large amount of data. Normally, when we have large amount of data set, now I am using for some real-time applications, some IoT weather monitoring or some healthcare system, some patient monitoring. So in such case, if I'm going with such a large volume data set, real-time analysis would be very difficult. Therefore, if I want to make the computational efficient deep learning architecture, what I will do first, I will make this some kind of BAT or binary BAT optimization algorithm to apply on this large volume features, and I'll make some feature extraction like binary BAT based feature extraction, and those features I try to give in the input layer neuron of the deep learning architectures, which makes it what the deep learning concludes early. Are you following me? That is one way. Other way, when we are making a better features, obviously your accuracy will be increased.
Okay.
So you can use in deep learning architecture like that. And other cases now wherever and all optimization is required, like wireless sensor network, energy high efficiency, energy harvesting, routering, this routing problem, and this localization. Where and all you can require all these optimization, you can use them. And other question, when large data set is not available, how to, I mean, synthesize the data set? See, most of the time, when the data set is a challenging problem, then using deep learning and other neural network based very, I mean, not very effective because there is no sufficient training data. So sometimes this data augmentation, semi-supervised learning models, and those one-shot zero-shot learning problems are effective for those type of problems because there is no much data set available. When there is no much data set available, there is no much learning happens over the deep learning architectures. Okay. Any other doubts?
Just in continuation with that,
Yes.
so I mean, I'm still not able to see how this optimization algorithms are helpful in extracting features. To say, not extracting or filtering the features.
No, not filter. See, when you have large volume, I mean, features exist in the data. Optimization, right? See, what do you mean by optimization? We have talked about the ant colony optimization, and of course, normally, if there is a large volume features exist, my job is with respect to the problem you are investigating. I would like to extract only few features which are really useful, and those optimized features I am going to deal with this particular deep learning architecture which you are going to extract, right?
Okay.
Now see, unless you do optimization, without optimization also your deep learning works. The only thing is what you have to increase the number of hidden layers, more and more hidden layers, more and more hidden layers. If you have better features, you may conclude early, right? What is the, because the moment I got some about 90% accuracy, then I can say that, but okay, I got the TZ classification, I can stop it. Otherwise, what happens? The more accuracy, the again you have to go with more hidden layer. So how do you optimize the features? Normally, see, deep learning is the other way, and feature optimization is different. The moment you go for better feature optimization, you will have the better classification accuracy in your deep learning.
So, I mean, exactly. How do we optimize the features, and what would be the objective function? What are
Then
we
we
trying
are
to
no
minimize?
that genetic algorithm, swarm intelligence, and then particle swarm optimization, bioinspired optimization. There are plenty of optimization algorithms like this. It's not about one particular algorithm. For example, I am into some load balancing or energy efficiency problem. Then what happens? I'm going to consider some sensor network data. Then I'm going to assign to certain gateways or base stations. Then I'm going to define what is my cluster head. Then I'm going to map it to certain suitable optimization algorithm. So which optimization algorithm, it depends on which problem statement you are investigating and what is your domain network. Then accordingly you can define, for example, some routing problem I'm going to optimize. Mostly what happens for routing problem, I use some ant colony optimization, where a group of ants exist and how they're going to optimize and find the shortest path. Then the same logic I'm going to use it for some this optimization of the nodes in this one. So it depends on what optimization, it depends on what data you are using, what application. So there are plenty of thousands of optimization algorithms. Indeed, you can develop a new optimization algorithm. In fact, we at Energo, we tried with a lot of new optimization algorithm. One is octopus based, and we are trying to improve dolphin swarm optimization algorithm. Binary bat also we are trying to improve. And what you talk about object functional, you have to develop your own object or fitness function for the optimization.
Okay.
So for that, first you study genetic algorithm, swarm intelligence, evolutionary computation model, particle optimization, and all the bioinspired optimization algorithm, and see what type of data you're dealing with. Then you identify. That will be fine.
The optimization algorithm, okay, choosing that we can do. What I'm trying to say in general, what are the objective functions? How do they look like? I mean, so we want to narrow down the number of features, and then we are trying to optimize which features we want to use. What are we trying to optimize it with respect to?
See, now when you take up some kind of data, like when you have some large volume features, now you just try to indicate, like if I take some genetic algorithm reproductive operations, like I'm going to find a fitness value for each of this particular object, like you can say feature. For which particular feature I'm going to get the high fitness value. I'm going to consider, like you can make some ranking model with respect to the features, number of features available, and try to see what exactly the operations you are going to perform on them, and for which values you are going to get the highest feature, highest fitness value. With respect to that, we can just optimize the number of features. Again, I'm telling you, it depends on what data you're dealing with. Genetic algorithm operations you can perform, and then particles from optimization, and you see the objective function value.
Okay, okay, sir.
Okay, then I think that's all. If you want, I can share the slides with you. Further, if you want, you can go through that. So if you have any doubts, you can just mail me also. I'm sharing my email ID. My suggestion is, when you, in case you want to go for optimization with respect to deep learning based solution, don't just take some existing optimization algorithm. You try to develop or design your new optimization algorithm. Then you can publish high quality journals rather than taking just some existing binary bat or some bat optimization algorithm and use it with some deep learning based architecture. You try to take some existing optimization algorithm and improve, or on the other side you try to propose a new optimization algorithm, because nowadays it's not very difficult, because plenty of options are exist with by just adopting some foraging behavior of a group of ants or birds or fishes, etc. I've just shared my email ID. Still, you have any doubts, you can contact me. So thank you. Thank you very much.
Okay, sir. Thank you.
Yes.
Thank you, sir.